Okay. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh, and welcome to week 7 of site planning. I know I should have asked Yusuf earlier about when he usually starts class. The class is scheduled for 7, so I started at 7. My mistake. So next week we will start at 7:30. I will start the class at 7:30 instead. Okay. Would anyone care to tell me what they have learned over the last 6 weeks, just to get me up to speed? Anybody? You know how awkward this is. Okay, well, I don't like to do this, but I think it seems that you leave me no choice. I'm going to randomly pick out a name. Mas Maulana, can you please tell me what Pak Yusuf has shared to the class over the past 6 weeks?
Yes, sir. Maybe last week, past 6 weeks, Pak Yusuf explained about the external site condition, the data, and the potential and problem, and then the external site analysis, and the site planning in general, sir. I think that's all.
Okay, great. Thank you very much for that. And may I remind everyone that we are in class, and well, it would be nice to see it. It would be nice to see it, or it would be nice to have this virtual session feel like a class where there is a dialogue. So yes, let's move it along then. I trust that you have all marked your attendance. So since Pak Yusuf has shared the external site conditions and external site analysis and external factors that may influence that influence or affect the way we plan our site. Over the next few weeks, I'll talk about internal site conditions, and then perhaps we will move on to site analysis, internal analysis of internal factors, and then moving on to how to develop conceptual design, and then further develop that concept. I'll talk a bit about construction documentation and project implementation, although that's not exactly what we're here for. We'll focus mostly on analysis, concept design, conceptual design and development, and then design development itself, until you can develop the finished product, which is a site plan essentially. So why is this? Why is the internal factors or internal factors or elements crucial? Well, when we talk about, I don't know if Pak Yusuf has shared this diagram with you, but when we talk about internal site elements, then we're dealing with physical attributes, biological attributes, and cultural attributes. Now, cultural attributes here does not necessarily mean traditions, does not necessarily mean traditions and cultural assets such as ceremonies and dance. No, not necessarily that, but cultural here is something like the regulations, land use attributes, and such and such. So we'll be focusing on these three: physical attributes, biological attributes, and cultural attributes within the site that will ultimately influence the way you plan, design, and develop the site. Why is this? And ultimately, I hope that the next few weeks will help you build a site inventory for your chosen site for the major assignment later on, which is something that I'd like to talk about as well at the end of near the end of this lecture. So build a site inventory to help you organize and categorize the elements that you will use for site analysis. So why is this such a crucial process or a crucial stage? Well, think about it. More than half of our population, more than half of Indonesia's population, the world, in fact, now live in urban areas. And to accommodate that ever-growing population, and ever-growing demand for living space, dwelling space, millions of acres of forests, wetlands, and grasslands are converted to build, urban, suburban, and ex-urban development. Now, this expansion of the built environment with this rapid expansion, if this rapid expansion is allowed to continue to grow with relatively little attention paid to sustainability aspects, then you will eradicate countless habitats. You will change, modify, and perhaps even destroy and fragment and destroy natural corridors that link terrestrial and aquatic habitats. And habitat loss and fragmentation. Because of habitat loss and fragmentation, ecosystems today are a lot more isolated from each other and less buffered from both human and non-human disturbances. So you've heard of stories, perhaps in rural areas where there are people-animal encounters, And some of those encounters are less than pleasant, at least. You have you hear stories of animals attacking people, animals maiming and harming children in villages. Well, it's not the animals' fault, really. It's the fault of humans that expand their settlement in such a way, at such a pace that they pay very little attention to sustainability, to how their activities impact the ecosystem and terrestrial and aquatic habitats. So ecosystems have both biotic and abiotic components, and the ecological structure and function of landscapes are influenced by the complex interplay of biological, physical, and cultural systems. Landscape ecology is a transdisciplinary science concerned with landscape structure, function, and change, which is something that some of you may delve into sometime in the future. Now, both basic and applied research in landscape ecology can help inform more context-sensitive land use planning at regional, community, and even site scales. So context-sensitive planning is something, context-sensitive site planning is one of the keywords that I'd like to highlight today. Now, the good thing is with the advent of technology and with the development of planning sciences, we now understand, for example, that when new roads are built in formerly forested landscapes, they can be barriers to the lateral movement of ground-dwelling animals, thus isolating endemic species and ultimately dooming those species to extinction at the local level and possibly at broader spatial scales. And conversely, roads constructed through previously undisturbed forests or other fragmented natural areas can serve as linear conduits for pathogens and invasive exotic species. So as I mentioned, we will be talking about, we will be highlighting this keyword right here, context-sensitive site planning, and we'll do that. And how do we do that? Well, we focus on site conditions, of course, and external site conditions have been discussed previously. So this week and the weeks following after that, we'll focus more on the internal site conditions. So every site is embedded within a landscape. When you, any site that you're developing is within a landscape. If you remember the built environment class, we have interior structures, and after structures we have landscapes. And a landscape is essentially, or landscape is where clusters of multiple structures are gathered together, and they cover a broader, if you remember the definition, it covers a broader area, and the lines between the built and natural landscapes are a lot more blurred in the landscape scale. So, and site planning is when you situate multiple structures together in an organized way, functional way, aesthetic way that forms a part of the landscape. So once again, every site is embedded within the landscape, and one of the key goals in site planning is to understand the site and its surroundings. Many site attributes such as vegetation type, slope, they in nature, they are unevenly distributed spatially. Some would be clustered over here, others would be clustered over there. Maybe they're spread out or distributed more sparsely. And some attributes, such as seasonal temperatures and precipitation, show very little spatial variation at the site scale. A lot of the times I get students or a group of students that give a seasonal temperature or site temperature analysis or a site climatic analysis. And when you're talking about a site, there's not that many variation between your site and the site next to it, climate-wise, because when you talk about seasonal temperature and precipitation, you're talking about a regional scale event or a regional scale attribute. So the site inventory that I was talking about is a focused process of collecting and mapping essential contextual information within your site. There are some features that might not be covered in this lecture because well, I hope that the previous lectures have covered external site attribute inventory. So coming to the context-sensitive planning theme, when we talk about context-sensitive planning, first of all, we need to look at the purpose. We need to look at the purpose of site planning. We need to look at the purpose, and then relay that with the site planning phase. And then these are some of the questions or probative questions that you can ask yourselves to help you with the inventory. So when your purpose is to describe your site, when you describe your site, then that's then the site inventory. A site inventory is the activity that you would take part in or you would conduct. So one of the questions that you should ask yourself when you're conducting a site inventory is, what is the ecological structure and function? So I would highlight these two keywords. So the ecological structure and function of the study area. First, that is the first and one of the first and foremost things that you need to understand. Then to understand the structure and function of the site, you need to ask yourself, how do the sun and prevailing winds move across the site? Are they moving in a northeasterly direction, or more of a north-south direction, or is it to the east and west, or is it more to, or is it southeast, northeast kind of thing? And then, are there any significant trees or plant communities on the site? Any specific vegetation, perhaps, that you need to pay attention to? And then, lastly, of course, where are the site's stormwater drainage patterns? If you look at the site's contour, then perhaps there are certain places where water can gather and form puddles, and these puddles do go away eventually. But if you let that stay in your site, if you don't engineer a solution to that, then perhaps these water pockets will inhibit your concept, your design concept, and the purpose of development. So moving on from description, after you've gathered all. Oh yeah, by the way, there are the questions are not limited. The questions are not limited to these three examples right here. So perhaps you will add one or two more questions to it, just to get more, just to understand the site a little better. Perhaps other than the stormwater drainage patterns, you might ask yourself about the slope, the angle of the slope and the contour of the site, and where which part of the site has more sun exposure, for example, and etc., etc. So after you've described the site, you move on to diagnosing the site and using the data that you have collected. Sorry, moving back to the site inventory phase again. So, for example, these questions, the questions here indicate the type of data that you need to collect. For example, when you look at you look at the first question, how do the sun and prevailing winds move across the site? Then, of course, you will need sun exposure data and sun exposure duration data, which I think nowadays you can get online. You can just punch in your site's coordinates, and you get this sort of data, the sun and wind. So that shouldn't be a problem. Trees or plant communities. This is something that you, well, like it or not, you have to visit the site. You have to have a look at perhaps official records, if there are any, of any particular vegetation that you might need to pay extra attention to, or such as perhaps endangered tree species or endangered animals and such. And the site stormwater drainage patterns, you have to look at you need contour data, and we'll talk about contour data and topography data a little later on. And then once you get all the necessary data, then you move to the diagnosis part, or the diagnosis phase, or site analysis, where you conduct a site analysis. So in the site analysis phase, you ask yourselves, what are the site's opportunities and constraints for implementing the project's program? So you're looking at these two, and you evaluate it relative to the project program. What do you want to build in your site? What would you like to achieve in your site? Are you building a theme park? Are you building a factory? Are you building a cluster of luxury houses, for example? So each design purpose have different requirements. So therefore, the site characteristics of the site attributes, the data that you've collected in the previous stage, will not exactly determine what you will build, but more of how you will build it. Some of the probative questions that you can ask when you're conducting a site analysis are, where are the potential site access points? So we're thinking of access. Where can we enter? Where can we exit? Where can we enter and where can we exit the site? Because of course that is then crucial when you. That is then crucial for safety measures, and perhaps even for efficiency, because perhaps there's a main road near your site which provides access, and then you exit to a more narrow rural road perhaps, or there's a possibility for an access point back into the main road, and so on and so on. So where are the potential access points? Perhaps up here and everywhere else. And can a new building be oriented to maximize solar collection? For example, if you have a building that sits on a slope like so, perhaps with the sun coming down here, then you and the sun's path movement, considering the sun's path and movement, then perhaps you will get some parts of your building will get more sun exposure, will get longer sun exposure, will get better sun exposure, or perhaps even overexposure to the sun, making it uncomfortable to conduct your activities inside them. So that's something that you also need to consider. And then, are there steep slopes that require stabilization? If a slope is, I think, up to 15 or 20 degrees is still okay, but I think anything more than 30 or 45 degrees, then perhaps if you're thinking of building there, or if you're thinking of engineering a site with such steep slopes, then perhaps you need to find a way to prevent it from causing trouble, such as landslides. So perhaps you might need to build a retaining wall. Pardon my handwriting. You need to build a retaining wall there somewhere on the site, so that you can achieve site stabilization, thus reducing the risk of potential disasters. And then, like a doctor, you're acting like a doctor. So what is your ailment? And then once your site describes their ailments, describes their attributes to you, you diagnose, you then diagnose the input from the data that they've provided, and then you come up with a prescription to not cure, but to enhance the site's properties. and you do that through drafting a conceptual design. So as I mentioned, you're not going to, the idea of site planning is not to change the site, but more of enhancing the site. So how can the new development, how can your design concept make a positive contribution to the community? How can it enhance what is inherently good, what is inherently positive about the site, and how can the new development minimize negative effects or negative externalities? Some of the probative questions for when you develop a conceptual design would be, are there natural or cultural site features that can be protected and perhaps even restored when need be? Can the site's development maximize good views to off-site amenities? Now, when we talk about off-site amenities, it's not necessarily infrastructure. Good views to off-site amenities. If you're building a resort, for example, mountain ranges, mountain views can be considered as a can be considered as an amenity, because that's a view, that's what you're selling. When you have a resort here, and the resort faces the mountain ranges, then that can be considered as the mountain ranges can be considered as off-site amenities. They're not necessarily yours because they're off-site, but you get what I mean. Maximizing good views towards off-site amenities and whatnot. And again, these are just example questions. Perhaps your site will require you to ask different questions, more detailed questions, I'm sure. And that ultimately it's the probative questions that actually will help you move along. And the more questions you ask, the more detailed data you can actually collect, and that way it's a lot. And the more information you can get for you can collect for site analysis or the diagnosis phase, then the better it is for you. The better it is, it will be for you to help make your decision. So I mentioned the three attributes of site inventory and three attributes of internal elements of a site. So there are physical attributes, biological attributes, and cultural attributes, all of which will go into a site inventory prior to developing the site. So what are the physical attributes? Topography, hydrology, soils such as soil type, geology, the rock formations and such, and microclimate. Biological attributes include ecological communities, any particular vegetation perhaps, wildlife. Cultural attributes would be land use, any open spaces perhaps. When we talk about site planning, it's not all about empty spaces. For example, imagine you are responsible for the redesign of the ITS campus. It is a built area sitting on top of a sizable piece of land, and so and you're redesigning it to maximize or to make the campus layout more efficient and whatnot. So of course there are built areas, there are natural areas, and then there are open spaces, which are perhaps a combination of both built and natural areas. And of course, other cultural attributes would be regulations, any specific rules that you need to adhere to, that you need to follow perhaps. When you're developing a site, I know some of the regulations that might affect your design would be the standards and spatial requirements for whatever function it is that you might design. Property here is not houses, no, but property here means the type of title, the type of ownership, whether it's full ownership rights or whether it's partial ownership rights and so on. Sensory perception, do you hear any noise? Do you smell anything when you're on the site? Anything in particular, any strong smells that might come from neighboring sites? If your site happens to be close to a landfill, then of course that would be a sensory perception thing. It smells of rubbish, for example, or if your site happens to be next to a factory, then if you want to build a resort, but your site happens to sit next to or nearby a factory, then perhaps you will need to do something about the sensory perception of chemicals, chemical aromas wafting through the air. And then, of course, other cultural attributes would be the infrastructure, but I think Pak Yusuf has covered that already. Now, all of these attributes make up the existing site and contextual conditions. So if you want, as I mentioned, if you want to develop a site, then you need to understand the site. And understanding the site means that you have to acknowledge and recognize the importance or the significance of each attributes and sub-attributes, subcategories, and each element of under the different attributes. So I know we'll focus primarily on this bit here. I don't know. I don't know if Pak Yusuf has already mentioned something about site programming, the goals and objectives of your site development, land uses and activities that you will introduce to your site, and the different phases of site planning. Mas Maulana mentioned earlier that Pak Yusuf has introduced us to site planning in general, so I assume that he's already mentioned this bit right here. That's okay. Again, we're not going to focus on that. We'll be focusing more on the existing conditions and what can we do about it. So when you introduce your design goals and objectives to a site's existing condition, you're essentially assessing the site's suitability, whether it's suitable. Is it suitable for a resort? Then if it's suitable for a resort, then you will continue to develop it. If it's not suitable for resort development, then perhaps you need to go back to the drawing board to adapt your resort's design to match the existing site conditions, or in extreme cases, you need to go back and look for a different location. And site suitability, as I mentioned earlier, consists of, when you're assessing site suitability, you're essentially taking a look at the constraints and the opportunities that a site has to offer. I'll give you an illustration of how constraints and opportunities influence or affect the overall development. If we take a look at this example, here we have a developable area. You have a site, and this is your developable area. At first, you're thinking, when you look at a map, this is the first thing you probably see, especially if the map doesn't contain satellite imagery. You're thinking, oh, okay, this is our location. The area is the area has been designated according to land use laws and everything as a developable area. So, okay, no problem. We have perhaps you're thinking of 50 hectares of land, maybe. Hypothetically speaking, you have 50 hectares of land that you can develop. But then when you conduct your site inventory, you discover that, oh, hang on, there is a specimen tree right here. So a specimen tree, or perhaps a cluster of vegetation that are endangered. So this area, this corner of the site right here becomes no build zone. Okay, well, your developable area then becomes slightly less than 50 hectares now. Not a problem. You continue trying to understand the site. You continue conducting your site inventory efforts. And as you walk along, you discover that, oh, hang on, there's a stream right here. There's a stream and a riparian zone where the river flows. There's a river flowing through the site, or a creek flowing through the site. And then you, after further investigation, you discover that the creek overflows during heavy rain. So it's, it doubles or maybe triples in size when it rains heavily. So okay, this area then becomes non-developable. But and of course, this area, this corner of the site becomes inaccessible because you can't get, for some reason, you might not be able to. It's not feasible to provide an infrastructure, or it's not feasible to build a bridge to connect these two sides. Okay. Then it becomes, then you realize that your development area becomes significantly less than, sorry, becomes significantly less than 50 hectares. You started out with 50 on the land use map, but once you assess the physical, cultural, and biological attributes, you discover that, oh, okay, well, there's no way that we're going to develop the entire site. But that's okay. Once you have reached a final verdict, a final diagnosis, then it then becomes a bit easier to develop your design. You may have a significantly less amount of land to develop, but it is developable. It is developable nonetheless, and these features such as waterways and exotic tree species or exotic vegetation, perhaps, that provide habitat for endangered animal species or exotic animal species, then become, at first they might become constraints to your site development, but then as you go along and you adapt your design, you adapt your concept, you can turn these constraints around and use them to your advantage as opportunities. And then, of course, perhaps throughout your comprehensive site inventory efforts, you discover that there is an off-site landmark. Think mountain ranges, or perhaps there is a valley. There's a valley there that is offsite, or perhaps there's a gorge with I don't know, with a huge waterfall. Then that becomes a landmark, or a potential offsite landmark, or potential view or attraction, sorry. So that is that is a very brief and a very overly simplified review or of what constitutes the site's constraints and opportunities. So we'll go on and see what the internal attributes are. So I need to remind you that site analysis goes well beyond mapping the site's existing conditions. It's easy for us to jot down the ecological what ecological infrastructures are there, what health or safety hazards are there, what natural resources are there. It's easy for us to plot the distribution of these attributes or elements, but when you conduct a site analysis, it goes well beyond that. Sorry. A site analysis is essentially a diagnostic process, identifying opportunities and constraints for specific land uses. So one constraint for one land use may not be the same for other land uses. For example, if you're building a house, then perhaps don't build it on a floodplain. But if you happen to have a floodplain, then perhaps you can build a recreational park, perhaps, so that a recreational or sports field, so that if when the site floods during heavy rain seasons, then the impact is not as devastating as when you're building a house. Because when you're building a house in a floodplain, when the floodplain gets flooded, surprise, surprise, when the floodplain gets flooded, then you're displacing people from homes because you put them there. But if it's just a soccer field, for example, or tennis courts, then when the sports facilities gets flooded, then you're not displacing anybody from their homes. All you need to do is clean up and perhaps some repairs, and that's it. So one site's constraint may be another site's or another land user's. Sorry, one land user's constraint may be another land user's opportunity, or may not be a constraint for other land uses. And the site inventory provides physical, biological, and cultural data for this program-driven analysis that you will conduct. As I mentioned before, some locations on the site may be unsuitable for development because of intrinsic physiographic constraints. When we come back to this, the specimen tree, the stream and riparian zone and such. So those are some of the intrinsic physiographic constraints. And other than the trees and stream, it could be steep slopes. It could be the contour and the topography of the site. So steep slopes, shallow bedrock. The bedrock is so shallow that perhaps it's super difficult to build on because, well, the surface is so hard to break. Surface water and wetlands can also be physical or intrinsic constraints. Other parts of the site may be suitable for development but are relatively inaccessible. Like this one here, it is part of the developable area, but there is no access because of the stream and riparian zone. So consequently, pockets of undevelopable area or undevelopable land can render the original development program unfeasible because of the prohibitive costs of extending roads and utilities such as bridges to isolated areas of the site. So because the area is isolated, it's not feasible to build a bridge to connect the two areas, then okay, either you look for something else or you readapt the design. So gaining a better understanding of the site's development limitations is a common reason for revising the project's program. So either you revise your design, you revise your concept, or find another place to build. Building in difficult locations requires more time, more resources, more money, not only during construction, but also after construction. Steep slopes, for example, they're a significant constraint for many developed users. Building foundations that are constructed on steep slopes are a lot more complex, and therefore they're more expensive to design and to build. And in locations where site drainage is poor, or where the subsoil is unstable, additional effort is needed to ensure the building's structural integrity. And perhaps you might need to carry out stabilization measures to stabilize the subsoil. So in a nutshell, taken all together, building on difficult sites is costly, and it also increases the risks of development impacts on both on-site and off-site. So yeah, acquiring development permits for difficult sites is usually complicated. So therefore, the potential impacts of the construction process, as well as the post-construction uses of the site. So it may be difficult for you to secure development permits for construction, and also for the operations, for operational purposes of the site as well. Some of the environmental impacts, if you choose to build on difficult sites, some of the environmental impacts can include soil erosion, groundwater contamination, and the degradation of critical wildlife habitat. So consequently, sites with significant physiographic constraints may be economically and perhaps even politically unfeasible to develop. So here are some development constraints that include ecological infrastructure. For example, ecological infrastructures include aquifer recharge areas, wetlands, surface water, critical wildlife habitat. I am of the mind to leave these ecological infrastructures alone. Don't build over them. A lot of the times we see property development occurring in former wetlands. So they would dump an immense amount of soil onto wetlands, and then that it's called land reclamation. They do reclamation and then they build on that land. So a lot of the times when you're dramatically or when you're drastically changing the ecological infrastructure, you will get negative externalities. One of the cases that I encountered on building on wetlands is the land surface continue to subside even after 6 months of reclamation. I know six months in my opinion, 6 months is not enough, and not enough time for the land to stabilize, because it's wetlands, of course. Water takes time to get out of the reclaimed land to make it stable. So if you're too if you are too quick to build on reclaimed land, then you will get land subsidence. And of course, the bedrock is usually located quite deep. So a lot of the times, developing on wetlands would cause you to spend a lot more money on structure, such as foundations. And you can't see the foundations, can you? So why is this house so expensive? Well, it's because it's got a really cool construction underneath the ground. Well, you buy your house for the facade and for the shape of the house, not necessarily for the foundation underneath it. So ecological infrastructure, stay away from it. Don't rely on hard engineering. Building pipelines over aquifer recharge areas, wetlands, and other critical ecological infrastructures. Leave them alone. Other constraints may be health or safety hazards, floodplains, earthquake fault zones, areas that are susceptible to landslides. Now, there are many mechanisms to preventing people from building on floodplains and other health or safety hazardous areas, but they could be through development permits and perhaps even insurance mechanisms. But sometimes people just want to build. People want to build on risky areas because of perhaps economic considerations or political considerations. There are physiographic barriers such as steep slopes, highly erodible soils and shallow bedrock, perhaps other natural resources, prime farmland, sand gravel deposits, specimen trees, scenic views. Perhaps you are building on a historic site and historic resources then become your constraints. Historic buildings, archaeological sites. I know a lot of buildings in Rome, or the development or Rome's development is hindered by these historic resources. I've been told stories of subway lines, metro lines in Rome. When they want to expand their network, they couldn't do it because when they went digging, they found an archaeological site underneath. So when that happens, the city government would then cancel the development permit and tell them to build it somewhere else, build around it, and they would get an archaeological team down there to document and inspect the archaeological site. So that hinders their development somewhat. Some ways, other times they've been quite creative in developing around archaeological sites. I know of one particular apartment building where they have a window, maybe more of a large hole that faces the public street, where people can have a look underneath the building to see that there's a temple or something buried underneath the housing development. Well, I guess yeah, they are quite creative in work and finding a workaround to the site's constraints. Cultural constraints or legal restrictions. Perhaps you run into restrictive zoning codes. Perhaps even restrictive subdivision ordinances, easements, and other deed restrictions. Other development constraints, they may be not as significant as the previous constraints that I mentioned, such as nuisances, noise from neighboring factories, from adjacent factories, perhaps odors from adjacent factories or adjacent landfills, and unsightly views. I don't really have any example for that for on-site reviews. Excuse me. So let's talk about the physical barriers and opportunities. So first of all, topography. Understanding a site's topography is, of course, essential in making good site planning and design decisions. Topographic surveys provide critical information about the site's biophysical context. So 3 key attribute maps can be derived from a topographic survey to graphically show variation in elevation, slope, and aspect. So when you, I'm sure you're all quite familiar with this sort of map. You can find it on Google Maps, where you see topographic lines that are spaced between each other. So you can kind of guess visually where the slope or how the slope looks like, and then from here you can sort of guess where water might run off, and from the different shades, when you compare different shades, say this area here and this area there, you can sort of guess or you can make a pretty good guess which of these slopes are steeper than the other. So this area here is steeper compared to that there. This one here is a good example of floodplains, potential floodplains, where there's a water runoff area here. This is where water collects from rainwater where rainwater gathers from different from the different elevations, such and such. So this sort of map tells you a lot about this sort of map, or the topographic map can tell you a lot about the site's characteristics. But of course, these are just the site's surface characteristics. And when you're conducting a site inventory and for site analysis, then you need to go deeper than that. However, as I mentioned, the topography map describes changes in elevation, and changes in elevation affect drainage patterns and visibility to and visibility from the site. Elevation data is usually portrayed on topographic maps as contour lines and spot elevations. So when I talk about contour lines, okay, you know what contour lines are. It's these orange bits here, and then spot elevations refer to these numbers, like so. So different. So these lines represent this line here directly there. That represents 523, I don't know, meters or maybe feet. Whereas this 660, this line 660 then signifies the differences in elevation between these 2 points right here. Oh, I should have chosen a different color. Sorry. For site planning purposes, an effective way to visualize topographic relief, such as this, is to create a choropleth map of elevation. Sorry. A choropleth map is essentially a topographic map, a topographic line map with colors. And the different shades of colors also signifies the different degrees of steepness or shallowness. Sorry. And usually to make it easier to relatively easy to view, or to make it easy to understand, topographic maps should have relatively few elevation classes. So not too many different elevation classes right there. What I mean by elevation classes is these two numbers right here. They're elevation classes. The rings or lines, other lines that are that lay between these 2 points, they don't belong to a particular elevation class, but sorry. So coming back to elevation classes, the range of existing elevations on and adjacent to a site determines the range of each elevation class. So for example, if the highest elevation on the site is 400 meters above a local benchmark, and the lowest elevation is 250 meters. So the map should be, well, this one here is 660, and but for the just to make it easier, for example, if the highest elevation is 400 from a benchmark, say 400 meters, and the lowest, let's say 400 meters above sea level, and the lowest is 250 above sea level. So the map must show a range of elevation of at least, what's the difference here, of 150 meters. So there's 150 meters difference between 250 and 450, of course. So you take this 150 and you then have a, as I said, don't have too many different elevation classes. 5 to maybe 9 elevation classes should do it. So just to make things easier and to limit the map's visual complexity, you can divide 150 by, you can divide 150 meters into six classes, which give you a difference of, which give you a result of 25 meter increments. So from, in other words, if this is the highest point on the map, so for example, if this line is the highest point on the map, which is 400 meters, and then there's a line underneath it that is 250 meters. So the next line, the next line should be should show a 25 meter increment. So 250 plus 25, and then another one is, of course, that's another 25 meters there, and then another 25 there, so on until you reach the 400 mark, if that makes sense. And to enhance the maps, to enhance your map's effectiveness, you can shade or color. You can shade or color each layer. Hang on, why is this not? Oh, there you go. You can shade or color each layer to represent the higher or lower elevations. Usually it's cooler colors for lower elevation to warmer colors for higher elevation. So perhaps up here, the highest elevation, you would shade it yellow, and down here, as a cooler elevation, you shade it in green. So you have a nice gradation, color gradation, changing from very bright yellow to very dark green, to show to show the contour or elevation. So what does the slope and elevation mean for a site? Well, a site's suitability for roads, walkways, buildings, and other structures is in fact a function of existing slopes on the site. In places like Hong Kong and San Francisco or other cities with relatively warm climates, development frequently occurs on sites with relatively steep slopes. In contrast, in locations with freezing winter temperatures, vehicles and pedestrian circulation systems on steep gradients can create a safety hazard from icy, sloping surfaces. Now, spatial variation in a site's elevation creates slopes that have both a gradient and orientation. Slope gradients can be computed and easily mapped with most geographic information systems and computer-aided design or CAD softwares. The range of each mapped slope class depends on the intended uses of the site and on the specific site and contextual conditions, of course, including soil characteristics, vegetative cover, and regulatory requirements. For example, to prevent significant environmental and aesthetic impacts, development regulations may prohibit construction on very steep slopes. For example, slopes greater than 25%. Soil stabilization and erosion controls may be required on moderate to steep slopes, anywhere between 8 to 15% or 15 to 25%. On the other hand, sites that are essentially flat, that are less than 1% slope, may be poorly drained. Water can linger there for long periods of time. Now, so each of these slope conditions warrants mapping, because these locations have significant site planning implications. I did mention that slopes greater than 25% are generally avoided to prevent environmental and aesthetical impact. However, extreme slopes can also be fun. Well, fun if your idea of fun is huffing and puffing up a really steep slope. This particular hill in Chichengkol is approximately 40%. That's a 40% slope. That's a very, very steep slope, and a lot of people seem to find that as an excellent idea, or they find that as a challenge to climb this very steep slope. Another example from abroad. This particular street right here, Gower Street, which is about 31%. Sorry, why did I change that to this? Which is about 31% slope, is also like this slope in Chichengkol, sort of become a magnet for people who seem to enjoy reveling in pain going up hills. So which is not a bad thing, actually. As I said, some people find extreme slopes to be fun. I don't like slopes. I did mention the word aspect just moments ago. An aspect refers to a slope's orientation. Orientation, or the compass direction that the slope faces. For example, north or northeast. And variations in slope and aspect influence the daily and seasonal solar radiation received by the site. In the northern hemisphere, north-facing 10-degree slopes will receive far less solar radiation than south-facing slopes of the same gradient. Now, the figure on our screen demonstrates the influence of latitude on the intensity of solar radiation striking the Earth's surface. And because the slope faces away from the sun, solar radiation striking a north-facing slope hits the surface at a shallow or a very acute angle. Consequently, sunlight strikes the slope in a more diffuse pattern, delivering to the surface less solar energy per unit area. Aspects influences the site's microclimate by affecting the amount of solar radiation striking the site. So if you look at this illustration up here, then if you compare these two, then you can see that how the different angles affect or impact the sun's exposure. This one is at a right angle. You can see this area right here where the sunlight is coming from, and here at a leaner angle, sorry, you can see that there's a lot larger area covered by the same light intensity and same light direction. So this is just to illustrate how the aspects of a site can influence the site's sun exposure. So, as I mentioned, this sort of thing then influences the site's microclimate. So steeper sites may be cooler than sloping, or relatively gentle sloping sites. So aspect influences microclimate by affecting the amount of solar radiation that strikes the site. Now, as with other physical attributes, the importance of a slope's aspects depends partly on the proposed use of the site. At higher northern latitudes, for example, a south-facing slopes are better suited for siting buildings that will incorporate active and or passive solar heating. Conversely, a north-facing slope may be better suited for ski trail development in order to limit the melting of snow in late winter and in early spring. Slope aspect, like slope gradient, can also be mapped with commercially available GIS softwares. Typically, aspect is classified using 8 categories: north, northeast, east, southeast, south, southwest, and so on. These are portrayed graphically by either shading or different shadings or different colors. More shaded northern slopes in the northern hemisphere are typically rendered with cooler colors or heavier hatching than other slopes with greater solar exposure. But that's just a technical thing. So other site conditions such as geology now. Surface geology is concerned with the structure, composition, and stability of the materials beneath and in some locations at the Earth's surface. Bedrock geology has a persistent effect on landforms due to the different rates of weathering that occurs on the soil parent materials. Landform classifications is useful in regional assessments, particularly for characterizing attributes that are difficult to quantify, like scenic beauty. Landforms, in conjunction with vegetation, define view sheds and can increase visual quality. Landforms also influence microclimate-like aspect. Stormwater runoff is also influenced by landforms, stormwater infiltration, and the distribution of plant and animal species as well. Soil formation, soil erosion, and soil deposition are all natural processes that involve rock fragmentation and weathering. And weathering occurs usually unevenly because of variations in the bedrock's chemical composition and structure. An important attribute of superficial or surface geology is the depth to bedrock. In some cases, or in some places, what we mean by depth to bedrock, or in our language, is tanah keras. So here we have the surface, and here we have the bedrock. And in some places, well, in a lot of places, there's a variation in height, or well, depth, if you prefer it, rather than height. So there is a variation in depth. So in some sites, this might be very deep, whereas in other areas the bedrock is situated not too far away from the surface. So very shallow bedrock. So if excavation for building foundations or for other site structures is planned for a site with shallow bedrock or glacial erratics, such as boulders, big rocks, you may need for special methods of removal, such as blasting. The cost of excavating a cubic yard or a cubic meter of rock is many times greater than the cost of excavating the same volume of soil, because of its properties, of course. Because these subsurface conditions significantly increase the cost of building construction, then the depth to bedrock is generally investigated. Geologic maps are usually publicly available, sometimes, not all the time, and these will help you identify the depth to bedrock and the sort of soil underneath your feet, essentially. Other than that, geologic maps can show you the age and distribution of rock layers and other geologic materials. A volume of rock of a specific type and age range is considered a geologic unit. Colors and letter symbols identify each geologic unit at or near the land surface. Therefore, a sandstone of one age might be shown as one color, for example, while a sandstone of a different age might be shown as a different color. A geologic map usually includes information on topography and cultural elements such as roads to help orient the map users. Volcanic activity, earthquakes, and landslides are relatively common events in some parts of the world, like our part of the world. These geologic disturbances are potentially devastating hazards that must be considered when planning new development in these regions. I'm of the mind that once a volcano erupts near your village, and move your village away. The locations of potential geologic hazards, such as landslides, are often mapped by the government agencies involved in preventing or minimizing natural disasters. So if you want landslide maps and other potential geological hazards, then you should consult with the regional emergency services, BBBD. Other site conditions, hydrology. Now, water circulates in the environment through precipitation, overland flow, infiltration, storage, and evapotranspiration. That's a big word. Groundwater moves by capillary action through the porous surfaces between unconsolidated land, gravel, and rock, and between the fractures and faults in the underlying bedrock. The water table or upper surface of the groundwater resource generally mirrors the surface terrain. In landscapes where groundwater is the source of local or municipal wells, groundwater pumping can substantially increase the depth to the water table. Topographic variation also creates drainage patterns, which you see here on this map, which in turn influence plant distributions. Now, the spatial correlation between vegetation associations and site drainage patterns is particularly strong in arid and semi-arid landscapes, where water is often the primary limiting factor on plant growth and distribution. Although groundwater vegetation linkage is more subtle in less arid environments, like our environment, for example, the continuous or seasonal saturation of soil can create wetlands. In coastal environments, brackish or saline surface and groundwater result in development of salt marshes and other distinct wetland communities. Without on-site and off-site mitigation, I think urban development or any kind of development can have significant impacts on local and regional hydrology. And these negative impacts include increased volumes and rates of runoff discharges, reduced time needed for runoff to reach surface waters, increased frequency and severity of flooding, reduced stream flow during prolonged periods of dry weather. So, land development, until relatively recently, involved the construction of buildings and paved surfaces that are impervious or nearly impervious. Now, these land cover changes substantially increase the risk of flooding, erosion, and other ecological impacts on properties downstream. Now, surface water pollution associated with stormwater runoff reduces the aesthetic, recreational, and ecological value of rivers, lakes, and other water bodies. And consequently, stormwater management has become a highly regulated aspect of the land development process. Land development may also negatively impact groundwater quality. When local groundwater is the source of a community's potable water, efforts must be made to ensure that on-site wastewater treatment systems and stormwater runoff do not contaminate local wells. Stormwater movement, infiltration, storage, and discharge should be considered in the site inventory. The assessment of hydrologic conditions require analysis of the site surface and subsurface features, including topography, vegetation, surface water distribution, land use, climate, soil forming processes, and deposits. Surface drainage patterns and potential flood hazard zones are typically mapped. These areas serve critical ecological functions and therefore comprise major development constraints. Aquifer recharge areas are also important to identify and protect from development. The primary paths of groundwater flow and the locations of groundwater discharge to the surface are also important. particularly in more rural locations. Subsurface geologic characterization may include the analysis of aquifer permeability, thickness, and discontinuities. Maps of groundwater and local geological conditions are particularly important in land use planning for rural areas without access to municipal water service. These site data can help determine potential sources of potable groundwater. Next site condition, soils. Climate, landform position, and parent material are key physical factors in soil genesis and morphology. Other factors include the growth, death, and decomposition of vegetation, microorganisms, and other biotas living above ground or within the soil itself. Soil properties are also affected by the previous and current land uses. For example, sites with a history of previous industrial or commercial uses may be contaminated with a variety of hazardous substances. And so investigation of a site's subsurface conditions is warranted if you are to reuse previously industrial or previously commercial uses and convert them to housing development, for example. If hazardous waste are present on the site, then the cost of remediation can be very, very substantial. Now, depending on the site's location and the intended land use program, the inventory may include attributes or soil attributes such as acidity or alkalinity, pH for short, permeability, erosion potential, depth to seasonal high water table, and depth to bedrock, of course. Soils vary widely in texture. They have various different textures. They have various different fertility, permeability, and other attributes that influence plant growth and development. Soils that are favorable for plant health reduce the impact of pests and diseases and therefore can reduce pesticide use. Soil erosion frequently occurs when vegetation cover is removed or substantially damaged during site clearing and construction. The topsoil losses from prior agricultural uses or other erosive forces can increase the cost of re-establishing vegetation on a site after construction. Moving on to the next attribute, climate and microclimate. Now, a site's expected climatic and microclimatic conditions can influence various site planning and design decisions, including building orientation and facade design, the siting and design of vehicular and pedestrian circulatory or circulation systems, selection and placement of plant materials, design of stormwater management and stormwater management infrastructure. Other than that, seasonal and monthly climate data should be available from national weather services. I know our Bureau of Meteorology. They do provide quite comprehensive and publicly available data. Other than that, local weather records can also provide additional information about the weather conditions that can be expected in each season. So I think climate and microclimate data for the site inventory shouldn't be an issue. What are the things to look for in climate and microclimate? Well, the relevant climatic data include temperature, maximum, minimum, perhaps day temperature, night temperature, day and night temperature variation, humidity, high, low, average humidity, wind, maximum wind speed, average velocity and wind direction, rainfall data, monthly precipitation totals, perhaps even going as far as 10-year maximums for a 1 hour and a 24-hour periods. Snowfall, if there is any, monthly total maximum for any 1 day, monthly average of solar radiation, and other potential extreme weather hazards. So moving on from the site itself, let's have a look at the attributes that can be found on the site. You need to look at, first of all, for ecological communities. So an ecological community is an aggregation of interacting species living together in the same place. Complex interactions among climate, soils, topography, disturbances, and the organisms themselves influence the composition and spatial distribution of ecological communities. And these communities are often named for the dominant plant species, which may be dominant because of either its physical size or its abundance. So, for example, the first thing that springs to mind when I think of ecological communities is hutan jati, for example. That's the first thing that comes to mind, not because of the size of the trees itself, but for the abundance of the trees. Landscape pattern, that's the spatial arrangement of habitat patches and corridors, along with the intervening land uses and land covers, usually strongly influenced biodiversity and other indicators of ecosystem health. Ecotones, the spatial boundaries of ecological communities, are especially important areas biologically. Animals may also find shelter in one ecotone, but seek food in another habitat. Now, the expanding built environment has dramatically altered the structure and ecological function of landscapes, not just here, but worldwide. Habitat fragmentation, for example, is a global problem that can be mitigated through the coordinated reintroduction of green infrastructure. Just by planting trees and gradually increasing a community's tree canopy, the negative impacts of habitat loss and impervious surfaces can be mitigated. So, and planting trees is also a stormwater best management practice. For example, in ITS, back when I was still a student at ITS, the trees, vegetations were surprisingly very scarce. And a lot of people were also hunting birds on campus grounds. And so after a few years being a student there, I think nearing or towards the end of my studies there, sorry, excuse me. Now, where was I? So towards the end of my studies, the management introduced regulations, planted more trees, and restricted bird hunting activities on campus. And what happened is after over the course of several years, we can actually see a gradual return of different bird species. I'm not an aviary expert, so I can't really tell you what species they are. Robins maybe, but gradual return of birds to campus because they have breeding grounds now. They have the campus, the tree planting program provided them with habitats. So such is a small example of what can happen when you introduce or reintroduce vegetation to a site. So land use changes often also impact habitat structure. For example, the pattern, size, and connectivity of habitat patches and corridors. Landscapes are a kind of dynamic mosaic that consists of patches like woodlots and corridors like streams, and sometimes larger, more extensive matrix like a cropland. And natural environmental corridors allow the movement of organisms between habitats on daily and seasonal timescales. These corridors also enable species migration over longer temporal and spatial scales. Gaps in environmental corridors, therefore, can be targets for restoration. Habitat connectivity is an important function of regional open space systems, so perhaps not necessarily within a site, but more of a regional scale, particularly in the context of climate change, which is altering the geographic range of countless plants and animal species. Riparian areas and wetlands serve important hydrologic functions, in addition to their ecological benefits, which include biodiversity. These natural areas also provide recreational opportunities, aesthetic amenities, and outdoor living laboratories for natural science education. Simply leaving natural areas untouched may not be enough to ensure their ecological health. Many forest bird species, for example, require habitats in large forest patches. The interior forest habitats are buffered from predators and from microclimatic fluctuations that are more common within forest edge habitats. And many animal species also need more than one habitat type for the different life cycle stages, such as reproduction and migration. So for millennia, plant and animal species have been adapting to habitats altered by human activities. Centuries of global trade, migration, and settlement have introduced thousands of non-native species to new environments. Now, these exotic and sometimes, or most of the times, invasive species. So other it can take form either in vegetation or as animals. So other so invasive plants such as vines and shrubs. For example, I think there's an estimated some tens of thousands species of exotic plants, animals, and microbes have become established in the United States, in both managed and natural ecosystems. God knows how much exotic plants, microbes, and animals have been introduced to our ecosystem through global trade paths and such. Nearly half of the species listed as threatened or endangered under the United States Federal Endangered Species Act are at risk primarily because of predation by or competition for food and space with invasive non-native species. Exotic species have also have substantial economic impacts. Annual expenditures for the control of non-indigenous species are estimated to exceed $6 billion per year in the United States alone. I think it would be interesting to find out how much we spend in controlling non-indigenous species to our country. Exotic species are usually successful colonizers, especially when the new habitat presents minimal competitive control that limit their growth and reproduction. You can limit invasive species in their native habitats by grazing or by predation. Competition for the same ecological niche helps hold in check the population of competing species. For example, the Melaleuca tree now one of the most invasive species in the Florida Everglades, was intentionally seeded there in the mid-20th century. Without understanding the potential impacts of the plant on Everglades ecology, the Melaleuca seeds were then dispersed in an effort to dry the wetlands and create land suitable for agriculture and urban development. Similarly, the eucalyptus tree was imported into California from Australia and planted as a new source of timber. In the benign California climate and with no significant natural competitors, the eucalyptus species has successfully colonized many of the Florida state's native oak forests and savannas. On sites with significant native plant and animal communities, consideration should be given to mapping the distribution of both native and invasive exotic species. Now, this information can be used in developing plans to eradicate invasive exotic species and potentially restore the degraded native communities. Now, in some contexts, the restoration of wetlands, prairies, riparian corridors, or woodlands may be feasible. Soils, hydrology, and vegetation maps are also helpful in selecting the most suitable locations for exotic species eradication and native species restoration. So, yeah. But I know it will be difficult for you to search for invasive species, but in a smaller scale, at ITS, for example, and perhaps in many housing developments throughout big cities, we can find invasive species such as rats, feral cats. You know, if they're not left in check, you might think, oh, well, cats are fine. But the problem with unchecked animal or invasive species is that they potentially carry with them pathogens that will lead to unpleasant diseases. Take COVID, for example, or if you look in the history books, say the plague carried by rats, the plague, Black Death, carried by rats. So we don't want invasive species, no. Now, moving on to wetlands. I put down here nature's nursery grounds, because wetlands perform a myriad functions that directly benefit society. Coastal wetlands, for example, are nursery grounds for shellfish and other commercial sport fish. Other species, such as migratory birds, depend on these habitats for food and cover. Wetlands also serve as natural retention areas for stormwater runoff and are often locations of groundwater recharge. Ephemeral wetlands have soils that are saturated for a relatively brief period each year, or in more arid landscapes even less frequently. Now, although in the dry season, these wetlands appear to have very little ecological value, during wetter periods, they are critical habitats for many migratory bird species. Now, wetland banking is allowed in some jurisdictions, some places for development mitigation purposes. This controversial practice attempts to create new wetlands in anticipation that existing natural wetlands will be destroyed through land development. Unfortunately, this practice is emblematic of a brute force approach to land development. Constructed wetlands typically develop far less biodiversity than indigenous wetlands. Another problem with this practice of creating new wetlands involves hydrologic context of both the destroyed and created wetlands. The loss or degradation of natural wetlands can alter local hydrologic regimes, increasing the flood risk and diminishing groundwater base flow into nearby streams and lakes. Wildlife. Obviously, when we talk about biological attributes, we can't forget the wildlife. And the populations of most wildlife species are spatially discontinuous. That is, the entire species consists of spatially dispersed subpopulations called metapopulations. Local scale extinction of metapopulations are an inherent property of ecosystem dynamics. It's a natural process in some cases, and this process involves temporary local extinctions, followed by migration and colonization by members of other metapopulations. It is essential, however, that the area in which a local extinction occurs remains a viable habitat for that species' future colonization and repopulation. If the habitat is destroyed or degraded, for that matter, or made inaccessible by intervening barriers such as roads, highways, then the geographic range of the species is permanently reduced. Wooded patches and stream corridors within urban, suburban, and rural landscapes are home to colonies of birds and other animal species assemblages. Conserving wildlife habitats within the built environment has benefits for meta communities, local communities of multiple interacting species, many bird and bat species, for example, prolific consumers of insects that are pests to food crops and people. Birds also have significant aesthetic value for avid bird watchers and casual observers alike. Some birds, not just birds, but some species, animal species, have become adapted to living or have adapted to living in the built environment. Take a look at pigeons, for example. Pigeons build their nests, or pigeons nest in atop high buildings, in roofs. Some owl species may actually prefer to live in farmlands. This particular owl, the barn owl, is actually no. This is not a barn owl. Hang on, this is a barn owl. The barn owl gets its name because it likes to live in a farmlands barn. Other birds, other native indigenous bird species, such as the kookaburra, for example, they have adapted in such a way to be able to live alongside human settlers. Possums, raccoons. Raccoons are highly adapted nicely to human settlement, but they're also often considered as an invasive species. Well, they're invasive to human settlement because they rummage through your garbage, like the feral cats do in our homes, in or around our homes. Moving on to vegetation, many communities recognize that trees are valuable natural resources that enhance the quality of life, sense of place. They also add to property values. Municipal street tree inventories commonly record tree size, species, and location. Increasingly common are municipal tree preservation ordinances that seek to protect trees throughout the development process. And in communities where orchards or vineyards contribute to a distinctive sense of place, development regulations can also protect these horticultural features. Now, plants are no doubt critically important elements in the built environment's green infrastructure. Trees can serve multiple design functions that directly benefit people and the environment. For example, trees help clean the air, create habitat for insects and birds. Trees can also serve as windbreaks, provide shade, and reduce the costs and environmental impacts of heating and cooling nearby buildings. By moderating the microclimates near homes and other buildings, trees also reduce the energy demand for air conditioning, as I mentioned previously. Trees also add significant aesthetic values by screening undesirable views or spatially defining outdoor rooms. Trees can also benefit public health by tempering the urban heat island effect and decreasing physical and emotional stress. I've read somewhere that green is a color that is very easy on the eyes. So the more greenery you see, the easier it is on your eyes and the more relaxed you can be. So thus reducing emotional stress. As physical amenities, trees can increase the value of real estate by, some say, as much as 15%. That's an arguable figure, of course. The International Society of International Society. Scratch that, I forgot about it. So context-sensitive site planning seek to integrate into the site plan where feasible significant existing trees and green spaces. In assessing a site's biological attributes, data on tree species, size, and condition are typically recorded. A key question to ask is if there are significant trees on the site, can these natural assets be incorporated within the development? Existing on-site trees require protection during the construction of buildings, utilities, circulation systems, and other site elements. Construction damage can kill trees outright or lead to their slow demise. Typical construction impacts include soil compaction within the tree's root zone, grading, for example, cutting or filling the soil within the root zone, and scraping the bark from the tree trunk and branches as well. Many tree species have a fine mesh mat of feeder roots within the top 30 centimeters of soil. At the very least, construction disturbances should not occur within the drip line of the tree's canopy, as you see in the figure here on the slide. In addition, the decisions including plant species selection can also help with on-site vegetation. So once again, coming back to this diagram here. So far, we've talked about the physical, biological attributes of existing site conditions that influence site suitability, which gives you a hint on what you can, what you should not, and what you can modify and what you should not disturb. Moving on to other on-site influences would be natural hazards. Natural hazards include atmospheric, hydrologic, geologic, and wildfire events that, because of their location, severity, and frequency, have the potential to adversely impact humans, their structures, or their activities. Natural hazards present significant risk to human life, of course, and property, of course, so therefore must be considered also in your site planning process. Now, the built environment's vulnerability to hurricanes in particular, we do have very strong thunderstorms here. In some places, hail as well. So the built environment's vulnerability to extreme weather is substantial because a large proportion of the world's population live near the oceanic coasts, and our country is our country is a country of I think the second largest or the second longest coastline in the world. So a lot of our population, a lot of our settlements is vulnerable to climate-related or climate disasters, such as hurricanes, thunderstorms, and tsunamis. With growing awareness of global climate change, the environmental and economic and human impacts of natural hazards have become an important public policy issue. And so you should consider natural hazards or potential natural hazards on your site. Now, if you ignore potential site hazards, that can lead to expensive, even deadly disasters. Now, earthquakes, hurricanes, and other natural hazards occur at infrequent intervals. The recurring nature of these events suggests, however, that it is not a question of if it happens, but when it happens. An event will occur in areas at risk. When an event will occur in areas at risk, earthquakes, for example, are dangerous geological hazards that impose shaking forces on buildings, bridges, and utility lines and other structures. Risk can be mitigated through innovative design and construction techniques, yet when the risk can be reduced significantly, for example, by not building in the most seismically active area, this is clearly a prudent course of action. So, earthquakes can be dealt with structural intervention or just by avoiding development in earthquake-prone areas altogether. Natural hazards that may impact a site are often weather-related. During periods of good weather, the dangers may be absent, but the danger is greatest when relatively infrequent but severe weather events do occur. Hurricanes, for example, they are weather events that have a significant land use planning implications. Hurricanes develop over water, so the risk they pose is greatest in coastal communities. And because hurricanes are long-lasting storms, their persistent rains can saturate soil, can exacerbate threat of local flooding and erosion if there is any landslides. Advances in building construction methods have reduced the risk of structural failures from storm wind loads, but however, the hurricane's main threat to life and property is storm surge flooding, so flash flooding from hurricanes. Storm surges associated with hurricanes create walls of seawater that are at least several meters above normal high tide elevations. Tsunami-like, if you so to say. Development in low-lying areas is especially vulnerable to the devastating social and economic impacts of coastal flooding. Moreover, the mean sea level is slowly rising and could rise up to, say, 1 meter over the next century as the Earth's climate continues to change. Flooding is exacerbated in watersheds where building rooftops, streets and parking lots and other impervious land cover substantially reduce the capacity of the landscape to retain and infiltrate stormwater. Managing the risks associated with climate change includes discouraging development and redevelopment in high-risk areas. It also includes increasing the capacity of upland areas to infiltrate stormwater runoff. So this diagram here that you see describe or illustrate the different natural hazards that may pose that may pose threats to your site. Could be earthquakes, severe weather, and flooding. So earthquakes, as I said, can be dealt with structural intervention, or you can avoid development altogether. But take a look at Japan, for example. They can't avoid development. Where are the Japanese going to move? But they do deal with earthquakes through structural interventions, thus reducing the risk of damage and injury quite significantly. Severe weather events can also be overcome through structural intervention. or you can also discourage development in areas where they will be potentially impacted by severe weather events. For example, coastal communities. You can't tell people to not build in coastal areas because some people actually depend on coastal areas for their livelihoods, say fishermen. But you can discourage further development from occurring in severe weather prone areas. Flooding can be dealt with through land readjustment, or you can also discourage development, or in fact avoid development in flooded areas or in flood prone areas altogether. However, avoiding development in these areas can sometimes be challenging because most of the times earthquake and severe weather prone, flood prone areas possess significant economic qualities and opportunities. And moving on to the other attributes, cultural attributes. And as I mentioned, cultural attributes does not mean traditions and cultural assets, but more to property ownership and property values and regulations and such. Most of the time, information on land ownership or land tenure is available in publicly accessible databases. Not all cities in Indonesia have publicly accessible databases on land ownership or land tenure, but we do have publicly accessible databases on land use. I think once we further develop the system, I'm sure we can also include in these records a certified survey map of parcel boundaries, a history of land ownership, and any deed restrictions or covenants associated with the property. Online digital maps and associated metadata are increasingly available commercially and through government agencies. This particular one is for, I think this is an example of Singapore, where you can view land ownership, view land lot, and search for its status. This one's privately owned, and you can dig deeper into the land use or the land ownership records, who owns it previously, and so on and such. Our regulations, of course, land use regulations are divided into national, provincial, and local plans and regulations. From the regulations or from plans such as RPJMN to provincial, which will then be translated regionally to RPJMD and other regulations and policies, and then of course translated into local plans and regulations such as citywide plans and detailed spatial plans. Other than these documents, we also have standards, SNE, to use as planning guidelines, which I will touch on in our next meeting. For those of you who were late to join, this is the QR code to mark your attendance. And while you are doing so, I invite you to perhaps share your thoughts and perhaps ask any questions regarding the contents that I have delivered today. You don't have to put your hand up. You can unmute yourself immediately if you happen to have any questions or comments. No? Well, all right then. I guess that is all I can deliver today. So next week, we will start at 7:30. I started this class at 7. We'll start at 7:30 as you've done so with the previous sessions. Until then, have a great day, everyone. Take care of yourselves and see you next week. Thank you again for joining me today. Until next week. Assalamualaikum warahmatullahi wabarakatuh.